gratifying to see all the people in the room today for this subject. Kudos to Meg and CRAN for drawing the attention to the issue. The last night's forum was equally well attended. I've been doing this. I've been on the Ocean Acidification Roadshow with Dick Feely for a number of years now, and often the room is 10 or 20 people. So it's really great to see this much interest growing in the issue. So what I want to do here with the opening remarks is just share from our perspective what the shellfish growers have been dealing with here in the Pacific Northwest over the past 5 or 6 years, and challenges that we've been having with our oyster seed production in particular. So when we first started seeing some seed failures, the focus was on Vibrio tubiaceae, a naturally occurring marine bacteria that causes mortalities in the oysters. And it was prevalent in the hatcheries and in the wild, abundant, and we were seeing failures both in the natural sets in Willapa Bay. So Willapa in southwest Washington is one of our major growing areas for the industry. Over 60% of the oysters on the west coast come out of Willapa Bay. And the Pacific oyster is a non-native species, but that's one of the areas that's naturalized. It's generally, historically, been pretty natural reproduction to supply seed. That seed set has failed since 2005, and this year there was a dabble of a set this year, really nothing significant. So between the natural set failures and the hatchery and the initial focus on tubiaceae, the effort was to try to deal with that tubiaceae. Filters were added to the Whiskey Creek hatchery to address that. A lot of effort and funding put into that, only to find out that the larvae were still dying because they got the tubiaceae in the water. So that's when we realized there was something else going on with the seawater chemistry that was causing those mortalities. And it was about that same time that Dick Feely came on the scene for us and was our keynote speaker at the Shellfish Growers Conference. I think that was in 2008. And I missed his talk. We got there just after and walked into a room full of very long faces. And I was trying to understand what had just happened. People had just heard Dick's talk and realized that what was likely causing the seed mortality was a problem way beyond their control, related to carbon emissions. And by the way, Dick told us all that water that's coming up in these upcoming events on the coast is 50 years old. So even if we can't convince the world to change the carbon emission policies, we've got 50 more years that are coming our way. It's going to get better. So, that essentially told us that in our lifetime, we are going to have to figure out how to adapt or work with these levels of waters, but also use the opportunity to try to draw our voice awareness about the issue, how real it is. So, this was one of the articles that appeared early on when we first started recognizing the acidification issues. Greg Willis done a nice feature article there in the Seattle Times to help get that message out. So just a broad picture of the West Coast industry here, lots of numbers, probably not readable for most of you, but I just want to highlight a couple of things. One is the West Coast farm shellfish industry produces about $117 million worth of shellfish a year, and Washington State dominates that production. And I'll talk briefly about why that is, but essentially it's because of our ability to own our tidelands. In fact, we've been able to do that since the late 1800s. It's really the foundation of why we dominate both the West Coast and the country in farm shellfish production. And then the other piece that's important to draw from this is how important oysters are to that production. And that's predominantly Pacific oysters, but 83% of the shellfish produced by the farms on the West Coast are oysters, and that's roughly 62% of the volume by dollars. So that's significant because, as it turns out, these Pacific oysters are the species that are most vulnerable to these corrosive seawater conditions. So real quickly, just to give you a picture of the industry and what happens there, this is just an image of Samish Bay to show the Bush Act tidelands, private parcels. So in 1895, the Bush Act and Callow Act allowed for the sale of tidelands to private ownership, specifically for the purpose of growing shellfish. If you did anything else with the land, it would revert back to this. So that's the foundation of our industry, and that ability to own those tidelands and gave you an asset you could take to the bank and grow against buy seed. So there's there's a number of areas. This is just one example of Billable Bay, and others would have similar maps showing the tidelands all parsed out into oyster products. So just some images of the industry here with the oyster seed production and what the oyster crops look like on the bottom. Some long line culture where we grow oysters off bottom, harvesting oysters, hand picking oysters and putting them into tubs for retrieval at high tide. That's what they're doing here, grabbing those tubs and bringing them in for processing. The clams, vanilla clams, another species that there's about 9 million pounds a year produced here in Washington State. Different types of culture. This happens to be my personal farm up in Samish Bay where I grow clams in rows under predator netting there in the sand. Dewey duck farming, our most recent species that we've been working on for the past 20 years. This is how we start them out. For the first year or so, they're in these nursery tubes to protect them from predators and drying out at low tide. So that's just quickly some images of what goes on in the industry. Here are where the hatcheries are located on the West Coast. You know, these animals are really fecund. They produce a lot of babies. And in the hatcheries, generally, because you take the predators out of the equation, you can produce a lot of animals. And so it doesn't take that many hatcheries actually to supply the whole industry up and down the West Coast. So Taylor's Hatchery is there in Dewey Bay. Coast Hatchery is right adjacent in Wilson Bay. And then the Whiskey Creek Hatchery out in the Oregon coast. And Dewey Tribe has a hatchery up by Bellingham. And then down at Oregon State University, the Hatfield Marine Science Center there, we have a research hatchery, a breeding hatchery down there. And it's been that facility, our hatchery, and the Whiskey Creek Hatchery that have really experienced the problems with the larvae production. So Coast Hatchery and the Lummi Hatchery have been more fortunate, and we're not quite sure why. That's some of the things we're looking at is to try to understand that, why not all facilities have had the same problems. What's happening is these upwelling events in Dick Field, I'm sure we'll get into this in more detail, but basically on the Washington coast, when we get north winds, it creates these upwelling events where the surface waters are pushed offshore and the deep ocean water comes up, and that deep ocean water is harboring this high CO2, low pH water that's corrosive to the larvae, and when that happens, for the Whiskey Creek folks, it's imminent. Right away, it's coming in their intake lines and impacting their larvae. For us, it's more delayed with our hatchery. We're more isolated in Dewey Bay, and it's a little bit of a different situation there. This is just a cross-section of an area off of St. George, California, showing how that corrosive water comes to the surface here. You can see the pH 7.6 rising up to the surface, and normally the ocean would be 8.1, 8.2 is where you'd like to see it. And then here the aragonite saturation, which Dick will talk about, another very critical factor. When that ratio drops below 1 is when your shells start to dissolve, and here you can see where this 0.8 saturation factor is up to the surface. So here's the impacts on the two key hatcheries here, Whiskey Creek and Taylor's, and this is important. I didn't explain, but Taylor's produce seed and sell seed to a lot of other companies up and down the West Coast, and that's really Whiskey Creek. That's all they do is produce larvae for sale to oyster companies up and down the coast. So these two facilities are really important, and not just our production, but a lot of other people's production as well. You can see what's happened from 2005 with the Whiskey Creek hatchery production. Taylor's production in 2008, 2009, our production was off 60% in 2008 and 80% in 2009, our oyster larvae production. So big drop there in those years in particular. We did some things, the white sections and the blue bars there indicate things that we've tried to do within our company to increase our capacity in our Kona facility and other hatcheries we have. It hasn't had the problem to try to offset the losses we've been having here in Dewey Bay. So you can see top right is what healthy oyster larvae look like, and then the bottom left is this photograph from the Kuihara paper. You can see that the left-hand side is what healthy oyster larvae look like, and the right-hand side is what they look like when they're growing in the high CO2, low pH water, how the shells essentially start to dissolve. And that's what's going on. The oysters are still growing their shells. It's just that it's dissolving faster than they can grow it. They eventually lose that race of pairs. So for us, it's been a story of panic and adaptation as this hit us, and so we obviously ramped up our efforts on research and monitoring and our data Sabot hatchery, and as I mentioned, expanded our ability there in Kona to produce larvae where we haven't seen the same problems. We've learned through this process that the early life stages are particularly vulnerable, so the first 2 or 3 days of the oyster's life, it uses amorphous calcium carbonate, so there's essentially 3 different types of calcium carbonate the oysters use to build their shells. The first 2 or 3 days, it's amorphous calcium carbonate that dissolves very readily, and it transitions to aragonite that is also pretty soluble, but not as bad as the amorphous. And then as they metamorphose, they transition to the calcite, which is quite a bit hardier. So if we can get them to that metamorpho stage, then as juvenile seed, we're kind of home free, at least for now, until the oceans get worse. So that's really been our focus, is those early life stages for the larvae, and work through that. The monitoring that we've been able to do has helped us dodge the problems. So this is a graph from Whiskey Creek, and when they have the upwelling events and that corrosive water is coming in, they don't spawn, and when they've got periods of south wind, they spawn like crazy, and basically with the monitoring, they know when the wind changes from the south to the north, they've got about a 24-hour period before that corrosive water's on them. And so they try to work around that, and with that monitoring, they've been able to increase their production and get back up, not to 100% by any means, but certainly stay in business, which has been really key for the West Coast industry. The natural sets in Willapa, I mentioned how those have failed as well. This is a graph of the data back to 1942 of the natural recruitment events there in Willapa Bay. Now, Trimble, I know he's here in the audience somewhere today. He's done a lot of work looking at this factor, and you can see, it's a non-native oyster, so it takes some unique weather conditions for it to reproduce and larvae to develop, and we don't get those every year by any means. So there's been breaks in the oyster larvae production throughout history, but it's somewhat unprecedented to have as many years as we've had here recently, and it's certainly gotten us to looking at what's causing it. We've always understood it to be weather related. If we don't have good warm weather or warm water, they're not going to spawn and survive. We had not previously looked at how the corrosive waters may be playing into those setting successes as well. Now I'm still looking at that. So as usual, with problems like this in research, the more you think you know, the more you realize you really don't, and that's been a challenge for us. We've done research and have a great collaboration with NOAA and other university scientists on how to work through this, but there's obviously other things going on. It's not just as simple as buffering the pH of the water and having our larvae survive. There's other things going on in that seawater chemistry that we don't fully understand yet, and that's where a lot of the focus is to date. Also trying to understand more about the Vibrio tubiaceae, because it's still a factor out there, and how the upwelling and these seawater conditions are playing into the threat to the tubiaceae, and then just trying to figure out a long-term strategy for the hatcheries to work through the problems. So are we canaries in the coal mine? Many people have heard this story, how the miners would take the canaries down and to test for dangerous levels of carbon dioxide. Hopefully the canaries perish first before the miners. And we'd like to think that maybe our situation with the oyster larvae is that for the rest of the seafood industry and those that are looking at marine life in the oceans. This is, I guess, just to try to think of what those ramifications might be for the rest of the seafood industry. The fact that 3/4 of the $4 billion ex-vessel revenue that comes from the commercial fishing fleets is from animals that either need calcium carbonate or prey on animals that use it. So, we're basically changing the bottom of the food chain here for this absorption of carbon dioxide on the oceans. So, this is a Sightline report that came out here this week. I just wanted to acknowledge this. This is a great report. I'll leave this up actually right now. Let you copy down that website. I encourage you to take a look. Jennifer Langston there with Sightline